Hello everyone, this is Professor Atif Iqbal from the Department of Electrical Engineering, Qatar University. My paper ID is 0229 and the title of my paper is Two Different Carrier Phase Shifted Space Vector PWM Techniques for Pole Phase Modulation Based 9-Phase Induction Motor Drive. The content of my presentation are the need for multi-phase machines, the introduction to pole phase modulation of multi-phase induction motors, the need for the performance improvement in pole phase modulation induction motor drives, then dual inverter fed 9-phase induction motor and the proposed carrier based PWM, followed by the results and discussions, and then conclusion. So multi-phase machines have several advantages compared to three-phase machine, such as lesser space harmonics, higher efficiency, better power distribution, improved fault tolerant capability, and reduced rating of the switches, and torque enhancement by injecting lower order harmonics. And the application areas for multi-phase induction machines are the more electric aircrafts, electric vehicles, ship propulsion, traction applications, and other high power applications. Pole phase modulation is a method for getting different speed ratio by varying the number of poles and phases in a constant ratio without changing the stator winding connection. In the pole phase modulated induction motor drives, it runs at high pole mode, then we get high torque for starting, acceleration, and gradient routes at low speeds. For low pole mode, high power for medium and high speed cruising. And in order to change the speed from pole phase modulation 1 to pole phase modulation 2, the multi-phase induction motor must satisfy the following criteria. That is, the number of slots should be equal to this 2 into P1 into Q1 into M1, where P is the number of poles in the first configuration and P2 is the number of poles in the second configuration. Q1 is the number of slots per pole per phase. M1 is the number of phases in the first configuration, and M2 is the number of phase in the second configuration. The ratio of the two poles is termed as K, and it is P2 by P1. So initially the machine is say running at a pole of P1 and with a number of phases as M1. Then it changes to the operation to pole P2 with M2 phases. Power is proportional to the torque, the product of torque and speed, and torque is also proportional to P by 2. So pole phase modulation is an effective method for obtaining different speed ratios continuously by varying both phase and pole number in a certain ratio. So the pole and phase, they are changed simultaneously. So the generalized equation is given here. Now considering this as a two-pole configuration, when it is operating as a 9-phase machine, the total number of slots in the machine is 36. The ratio of P1 and P2 is 1. Now, if we change the excitation of this coil, then the number of poles changes like this. So it was a two-pole configuration earlier. Now, due to change in the excitation only, we are not changing the winding. Just the excitation is changed. The direction of the current is reversed. Then the pole changes to 6. So initially it was working as a two-pole machine, north and south, and now it works as a 6-pole machine. Here it was operating as 9-phase, and now this is operating as 3-phase. So this ratio is 3. And this is the north pole. Then due to reversal of the current in this coil, it becomes south pole, and then it is north pole, and once again this is south, this is north, and this is south. So 6 poles are formed, and this is the basic of the pole phase modulation. So two conditions are to be met for a symmetrical pole formation. The pole must be in such a way that the P1 should be less than P2. and the ratio K must be a positive odd integer. So in pole phase modulation technique, for meeting the high torque demand, there is an increase in the number of poles, and that decreases the number of, and there is a decrease in the number of phases. So since the number of phases is decreased, this causes higher space harmonics in air gap. And if the space harmonics are higher, the torque ripple in the machine is high. So this is the shortcoming of the pole phase modulation scheme, and this we are going to improve. Then due to two-level voltage source supply, there is a further increase in the torque ripple, and the semiconductor switches and source of the inverter, that they are increases with respect to the number of phases in the multi-level inverter. So the considering the converter side, due to the space vector modulation, this is well known that if we use three-phase space vector modulation, then it enhances the DC bus utilization by 15.4% compared to the normal carrier-based scheme. And for five-phase machine and five-phase space vector modulation, it increases the DC bus utilization by 5.15%. And for 9-phase, it is 1.54%. So there is a lower DC bus voltage utilization because of the higher number of phases. So this was 3-phase, 5-phase, 9-phase. So as we increase the number of phases, the DC bus utilization is poor. So what we are going to do is that we are, although operating a 9-phase machine, but we implement 3-phase space vector modulation in this, and hence we obtain the same enhancement in the DC bus utilization as we get in the 3-phase system. So for addressing the limitation of the pole phase modulation induction motor drive, two different carrier phase shifted space vector modulation techniques are proposed. The objective of the work are to propose a carrier phase shifted PWM to generate multi-level voltage, as well as improving the harmonic profile by cancelling the lower order center band harmonics, and improving the torque ripple when working in 3-phase 12-pole mode. So conventionally, if we are operating this as a 3-phase 12-pole mode, the torque ripple will be high, but we are improving torque ripple in 3-phase 12-pole mode operation as well. And there is an enhancement in the linear modulation range when it is operating as 9-phase 4-pole mode when compared with 3-phase carrier-based space vector modulation. So this is explained here. We have 3 groups of windings. There are 9 windings. They are divided in 3 groups called Group 1, Group 2, and Group 3. So when operating as 9-phase 4-pole mode, then the windings, they are excited as 0 degree, 120 to 40, 40 like this. So this is phase A, this is phase B, this is phase C, then this is phase D. So this is how we excite the phases, and each group has 120 degree phase shifted winding. So this is like Group 1, this is Group 2, and this is Group 3. So since we have 3 groups, so each group we implement a 3-phase space vector modulation, and this is the excitation scheme. And when we use this machine as a 3-phase 12-pole mode, then this ADG, they are all together. They are excited with 0 degree. Then BEH, they are excited with 120 degree, and CFI is excited by 240 degree. So this is the proposed configuration for 3-level inverter fed 9-phase pole phase modulation based induction motor drive. So here this is 3 windings, 3 windings, and 3 windings. This is supplied by dual 3-phase inverters. Here 3-phase inverters and dual 3-phase inverters. The DC link is common here, VDC by 6. Here the DC links are separate, and VDC by 6, VDC by 6, and VDC by 6. Then there are 2 bidirectional switches, B1 and B2 are used. This B1 and B2, we'll see how it operates. So this is how we form 3 possible level in the across phase winding A. So this was the switching scheme, and that produces VDC by 6. And this is the switching scheme when we obtain 0 voltage across the winding, and this is how we obtain minus VDC by 6 Na. So 3 level voltages is created across the motor windings. So when 9-phase 4-pole mode, this phase A is excited by 0 degree, phase D is excited by 120 degree, phase G is excited by 240 degree, and B1 and B2 is off. So due to B1 and B2 being off, so this is acting as a 3-phase, this is acting as a 3-phase, and this is acting as a 3-phase. So we can implement space vector modulation that is implemented normally in 3-phase. That same we can apply here. So we, although this is a 9-phase machine, but we are implementing 3-phase space vector modulation in these 3 groups, and hence we are able to enhance the DC bus utilization by 15.4%. And there will be a presence of the common mode voltage, but because B1 and B2 are off, so there is no common mode current. So 3-phase 12-pole mode, this phase A, D, and G, this is supplied by 0 degree phase shift, and B1 and B2 is on. So that's the operation when it is operating as 3-phase 12-pole mode. So 2 carrier-based PWM schemes, they are proposed here. This is called carrier phase shifted PWM1, which is the combination of level shifted and phase shifted. So when operating as 9-phase 4-pole mode, either we use level shifted PWM or phase shifted, either of the two we can use. While in 3-phase 12-pole mode, we have to improve the harmonic performance. So a combination of level shifted and phase shifted is proposed here. So this is the novelty in the work that we implement with the 6 different carriers and 2 different like it has both phase shifted as well as level shifted. Now carrier base phase shifted PWM2, and so this is carrier phase shifted PWM1, this is carrier phase shifted 2. So here 9-phase 4-pole mode, and all of them is used phase shifted, while in 3-phase 12-pole mode it is also used in phase shifted PWM technique. And here are the reference for the carrier, reference and carrier for 9-phase 4-pole mode. So this is carrier phase shifted PWM 1, and this is for carrier phase shifted PWM2. And these are the different switching states. So we see that when the operating as in PWM1 mode, this is 9-phase 4-pole. This is the PWM2 for 9-phase 4-pole. So when the reference is greater than carrier 1, then this is the switching states, and when it is greater than when it is less than C2, then this is the switching states. And similarly for phase shifted, this carrier phase shifted PWM2, this is the switching table. So here this is the 3-phase 12-pole mode operation. So we implement the combination of phase shifted and level shifted. So there are 6 carriers, so 3 here and 3 here, and they are level shifted. And this is the carrier, this is the reference signal. And here the switching tables are shown, and this is all like phase shifted for the implementation in 3-phase 12-pole mode. So this is 2D view of the machine, and this is 3D view of the machine. The machine is simulated in ANSYS finite element software. So a 5 horsepower machine with 4 number of poles and 50 hertz. And these are the different parameters that are used for the analysis and simulation. So this is the animation for the flux line distribution when operating as a 9-phase 4-pole mode. And this is the flux line distribution for three-phase 12-pole operation. These are the experimental prototype which is tested in the laboratory. We have a 9-phase machine with 5 horsepower rating, and this is operating in 1:3 speed ratio. So the 36 slot in this stator and 49 in the rotor. Full pitch winding, coil pitch 9, DC link voltage 70 volt, switching frequency of 2 kilohertz and modulation frequency of 50 hertz. And these are the physical dimension of the machine's stator. So this is the experimental voltage and current waveform for 9-phase 4-pole mode without isolated neutral. So when the neutrals are not isolated, we see that there is a third harmonic current that is present in the machine. And then experimental voltage and current waveform when operating as 9-phase 4-pole mode with isolated neutral. So when the neutral is isolated, then we see that the third harmonic is finished and we have a nice waveform. This is the waveform for 3-phase 12-pole mode operation when it is carrier phase shifted PWM1 is used, and this is the current waveform. This is the voltage waveform. This is the harmonic spectrum. When we see the voltage across the winding, we see that it has multi-level output, but the levels are not symmetrical. And this is the harmonic performance and for carrier phase shifted PWM1. And this is the harmonic spectrum when we are implementing carrier phase shifted PWM2. What we see that here it is a clean waveform. The switching harmonics appearing at 12 kilohertz, while it appears at 6 kilohertz and when operating in carrier phase shifted PWM2. So this is PWM1 is considered better compared to PWM2. And this is the simulation result for 3-phase 12-pole mode operation when supplied by 2-level voltage source inverter. And we see that the ripple in the torque is quite high. This is for 3-phase, but for 9-phase, the ripple is low. And when we are implementing the same with 3-level voltage source inverter, when we are supplying the 3-level voltage source inverter, the harmonic, the ripple profile is better for both 3-phase as well as 9-phase machine. And this is for 3-level voltage with PWM1. And we see that the ripple is further improved. So in this work, a dual inverter-based, multi-level inverter-fed 9-phase pole-phase modulated induction machine drive is presented. The proposed pole-phase modulation induction motor drive is modulated with different carrier phase shifted PWM. Both level shifted and phase shifted PWMs are effectively employed. And the key conclusions are that the linear modulation range PPM-based 9-phase induction motor drive is improved by 15.4% as compared to the normal carrier-based PWM scheme. And this is the same DC bus utilization improvement that what we achieve in general for 3-phase system. So with the proposed carrier phase PWM, both the number of levels and harmonic profile of active phase voltages are improved. The multi-level voltage generated by the proposed carrier phase shifted PWM improves the performance of PPM drive. And the 9-phase 5 horsepower machine is examined and it is validated using multi-level schemes, and both like simulation and experimental results, they matches each other. And that's it for this paper. And this is myself. This is my postdoc, Dr. Pratap. This is my PhD student, Mr. Mehraj. These are other postdoc, Dr. Pandav, and my colleague, Dr. Muhammad Al-Hitmi. So we are all the authors of this paper. And thank you very much for the patience. And this paper is a part of the research project funded by Qatar University under Qatar University High Impact Research Grant Scheme.